Guys, today's topic of discussion will be overfitting and underfitting, and we have previously seen uh, what is supervised learning and what does a flow of machine learning problem looks like. We first gather the data, then clean the data, then we will do some visualizations based on that independent and dependent variables. Then we will divide our data into two parts, one for the testing, one for the training. Then we will try to build a model on the training data set. We will train our machine learning model using the training data, and then we will test our developed model on the testing data set. And if we are okay, we are happy with the performance of our machine learning model, that we will evaluate using some evaluation parameters, which we will discuss today after this topic. We are ready to deploy our machine learning model. So these are two terms, underfitting and overfitting, which frequently appear in any of the sessions, any of the machine learning applications. So what overfitting is, so as the name suggests, overfitting, you can think of overfitting as something which is so you can think of overfitting as a cloth which is very tightly following your body curves, right? So if you are wearing a very tight t-shirt, very tight trousers, and which is following your body very tightly, your whole physique is visible, that you can think of that clothes to be overfitting, okay, which is following. So that particular cloth may not cannot, that t-shirt can, nobody else can wear it, because it is like very specifically designed for your body. Okay, it is following your shoulder, your waist, your biceps. Okay, so it just fits you only. uh, in terms of data, in terms of machine learning, the model which fits too much to the noise from the data, okay, is called an overfitted model, or this often results in low error on training sets but high error on validation sets. So we have this term here, the model which fits too much to the noise from the data, right? So what is noise in terms of data? So if I'm speaking to you and if there is some music running in my room, then then that music or the sound from the loudspeaker or from the surroundings is acting as a noise. Okay, noise, why? Because you want to hear my voice, not that music. Okay, so anything which is any information which is extra from the desired information is termed as a noise, is termed as noise. Okay, so in a data, in with respect to data, so for and machine learning, so the model, the data point, and there is a model which is predicting the data point's value, or like there is a desired value of a data point, and there is some extra and there is an actual value of data point. So that noise, or you can think of noise as the error, how much my data value, my actual data is deviating from the desired value or the expected value. Okay, because the data we collect from the actual world, and using machine learning we predict what this should value be. So what should be the rain, what should be the amount of rain for tomorrow? There is a model that will predict the rain for tomorrow, but after recording actual rain tomorrow, I can measure, okay, my model said this much of rain, but actually it only rained this much. So there is an error. So for the machine learning and data, noise means error, difference between the actual value and the predicted value. So any model which fits too much to the noise is said to be a overfitted model, and this often results in low error on the training data, but high error on the test or validation sets. So it means like when you are doing training when you are building the model using the training data set, the error will be very less. But as soon as you try to test your model on a test data set, the error will be very much. We will look at this in detail. Okay, so suppose this is my data, some variable x, and this is my dependent variable y. I want to predict y by using the values of x. This is what a distribution of my data looks like. Right, next, a good model will look something like this. So it is a smooth curve. I want to get the equation of this curve which can explain me like this. So y can be explained as a function of x. Okay, so here is my x, like this, some equation I want. So this x, this thing can be a curve in this case, or a straight line, or or any kind of a curvature, right? which I can write mathematically, like y is equal to some 5 times x plus 14. Okay, so I am getting the value of y in terms of x. Okay, so this can be some actual data. This is how a good model may look like. But if you want to look an example of overfitting, so this is what an overfitting data looks like. See, like this zigzag curve is passing through all the points, and this data is a training data set on which I am training my model. So this equation or this curve is perfectly fitting the training data set, right? Because it is passing through all the points, unlike this curve. So this curve is not actually touching any of the data points, or it is not passing through the actual data points, but it is kind of giving me an estimation with some error. So for this point, this is the error. For this point, this is the error. For this point, this is the error. Okay, this is the error. But if you see overfitting, it is exactly passing through all the data points, meaning it is too much fitting to the noise. Okay, so like this thing is the noise. So like this is my model, the green line, and this little deviation from the predicted value is the noise, right? But in this model there is no noise. Why no noise? Because my model is predicting exactly the value that I want. Okay, because all the data points, my curve is following all the data points, right? But suppose I want to now find the value of this x. What can you say the value? Whether it will be here, whether it will be here, whether it will be here or here, right? So whenever suppose this model is built or using training data set, and when I'm going to test this on my testing data set, it will like fail terribly. It will give me like 90% error, 95% error. It will go totally wrong, because like what is the trend? Can you see any trend? Like whether it will go up, like it will come down like this, or it will come down like this, or it will go up here. There is no trend. But here I can see. So the curve is going from here, then maybe like see, it can go something like this. Okay, so for a long further future values of x, I can easily predict what should be the y value. Like it will be here, here, or here, because I can follow the trend. Here I cannot follow the trend, right? So this is called overfitting. I'll see now for this particular point, just one point, the predicted value is coming over here. So there is too much error. This is all error in prediction, right? Suppose this point comes, so the next point comes here. So for this point, the error will be this much, right? But you can see like this whole data is following some other trend. Let me remove this. Okay, so for this particular point, this much is my data, right? So it is giving me lot of, so if I were to make a prediction for this value of x, give me the value of y. So my model will give me this y, but actual y is this one. So there is an error of this length, or you can say this much is the error, right? This is called overfitting. Because and suppose it is in other words, to understand overfitting, it is like just memorizing all the question answers, all the, suppose it is like I gave, my input is 2 and output is 4. My input is 3, the output is 6. Okay, my input is 5, the output is 10. Can you tell me what is the function that is mapping this value to this? What is the function that is mapping? This is my input.
2.
2 times, right? 2 into this. So my function is y is equal to 2 times of x. Okay, but uh, suppose so because this can be called a generalization. So like this whole thing, I can take 1000 values, 1 lakh values, but if I know this function, I do not need to store anything. I do not need to memorize anything. Okay, I just know, okay, whatever you give me x, the output will be 2 times that input, right? That can be the output. But suppose if a student doesn't know, like a small kid, like small children will do, they memorize all these value. When he says 2, I have to answer 4. When he says 3, I have to answer 6. So when so these are the data points that he has seen. Okay, 2, 3, 5. So if there is a graph, so for like 2, 3, 5, the values are like 2, for 2 is 4, 3 is 6, and 5 is 10. Okay, so for like all of us are very intelligent, we can draw a straight line, like y is equal to 2x. This is a trend. But for a kid, he can do, okay, for 2 this is the answer, for 3 this is the answer, and for 4 this is the answer. So for him, the trend can look like, okay, I just remember the input and the output values, I can memorize all of the things. But whenever he sees some other value which he has not seen before, like 21, 52, 79, what will be the value of the output, he will get confused. Okay, it is like memorizing all the question answers behind the answer, behind the chapters in the book. But whenever teacher changes some of the data values, the student gets completely baffled as to what how to approach the problem. So in with machine learning, we want to generalize any underlying pattern. We want to get the trend, not exactly rote learning. So because computer can do rote learning easily, because it is computer is very good at doing calculations and memorizing things. So we don't want our computer program to do that for our system. Okay, so this overfitting we needs to avoid, because which with this kind of a zigzag curve, I cannot predict what should be the coming next value. Whatever the value I have seen, I have used for training, it is very good. Yes, this is predicting the all the training values, but what about the testing data set? How can you use this equation, because there is no equation of this thing. Okay, so now comes next thing is underfitting, which is just the opposite of overfitting. So overfitting is overfits. Okay, and underfitting is like it underfits. Suppose your size is your waist is 34 and your t-shirt size is 42, but you are wearing 45 and 38. So obviously you can wear that, but there, it is not following you. Anybody can wear that t-shirt. Anybody can wear that shirt. It is not specifically for your particular body. Okay, so a good fit will be like some like a jeans of around 34, 35 and a shirt of 42, 41, 45, 40, 43. Okay, only this is the good range of your dressing for this is the best size for your particular body, right? So underfitting is like wearing very loose clothes, and overfitting is like wearing very tight clothes. Both of them is not required. So model does not capture the underlying trend of the data and does not fit the data well enough. Okay, so it has low variance and high bias. So these are like two terms that we keep seeing in machine learning: variance and bias. Underfitting is often a result of an excessively simple model. So when we are like very simplifying the model, using the very simple model, so it is not explaining the model completely. Okay, so it has low variance. So variance is the deviation. It is that for, if you remember from the recall from the statistics class, variance is you take each data point, take its difference from the expected value, or you can say the mean value, then you square that value, and you do this for all the values, all the data points, and you sum them. That is the variance. Okay, or in general term, variance is the amount by which my model will be disturbed if I change all the training set data. Okay, so suppose for some values like 1 to 10, uh, not 1 to 10, suppose for some value of x, I am getting some value of this is my relationship. Okay, suppose I change all of these values, so like will this curve remain same or it will change? So by how much amount it will change, or how much my model depends on the training data. So changing data, what will be the effect on my model? It is as simple as that, right? Suppose for the 10 examples, it is giving me a model like this. For if I now change all the 10 examples, again I give new 10 examples, so what will be the model? So like whether its shape becomes more sharp, or it remains the same, or becomes a little bit shallower. So this type of variability in the model, uh, uh, based on the input data, is called variance. Okay, a figurative term. Bias is a term which takes care of the form, like what will be the form. So whether like shape is going to be like this, or shape is going to be like this, or shape is going to be like this. Like what should be the what will be the shape of my data? How will my data look like? Form of the data. So for a straight line, for a straight line, for a straight line, sorry. So if this is a straight line, so like this term will be your bias. Okay, so how much your line will needs to move in up and down direction. Okay, and your variance will be like, suppose my data point is this, data point is this. So suppose these are all my data points. Okay, like this. So this data points, this variance is this much, the distance square of these distances, right? For all of these points, sum of square of the distances from the mean line, right? This is the variance. And for suppose this is my for the same line, now I'm taking into consideration these points. Okay, so for these red circles, this line is giving me higher variance, because this distance is more, right? So that means my model will change if I change this data, right? The circles, if I change, the model will change drastically. So because that means this line is not a better prediction of these circular points, because there is high variance. The distance from the pod of all the data points from the mean line is very high. Okay, so it has low variance but higher bias. So let's take an example. Suppose this is my again the same data y with respect to x. So underfitting will be like I'm trying to predict this variation in data or this distribution of data using just a straight line. So straight line is fine. So right, suppose this can be, so this y can be the weight, right? So weight has an upper limit like 90, 100. After that you cannot have a, you do not see, if you take a sample of 100 people, you will not see like 100 kgs or 150 kgs is common. Okay, so my weight, and suppose you can say this is the age. So age can be, so this will vary between what, uh, if you're taking the sample of working professionals, so it will vary between 25 to 60. Okay, so your height will be somewhere here only, remain here only. But if you are using a straight line to predict this thing, you may get wrong, because at this, if you for this value of x, maybe like here you are want to predict, so this is going to give you this much of value, which is not the case, right? So it is a simpler model for this kind of a distribution, this kind of data. So such kind of a fitting is called underfitting, where my model is not able to explain the data, the variation in data. Okay, and we are using a simpler model to predict the variation. Okay. So like this data was very easy to visualize, but how can we manage see underfitting and overfitting when dealing with multidimensional data? So multidimensional data means when, so suppose here I just have one row, I want to predict y based on x. So it is, my data will look like two column data. Okay, I want y based on x, but suppose I have multiple rows, multiple columns. Okay, height, weight, age, and based on that I want to predict some marks or something like that. So I have multiple columns and I want to predict just one column out of them. So it is called multi-dimensional. Like, so it is two-dimensional. The one dimension, so one dimension is this, one dimension is this, the third dimension can be here, right? But what about it has a force parameter? How can I represent this? I cannot do that on a 2D screen. I cannot do that in a 3D screen also, right? So I need some kind of a way to figure out. Okay. So what trick that we use, or what is the accepted procedure to do that is simple. We have to measure the error over the training time. Okay. So basically, whatever, so I have a model, my model will give some prediction for some value of x. Okay. And there will be, when I'm doing the training, I also know what should be the actual value of x, or what should be the actual value of y, and what is my predicted value of y. So I can always do y minus y predicted, y actual minus y predicted to get the error. So with time, that with training time, the error will decrease. Okay, so first iteration, it is some error. With next iteration, third iteration, fourth iteration, fifth iteration, or you can say the time of training, because training takes time. Remember that example of the trainable, teachable machine. When I gave pictures of myself and the robot, it took some time to build the model. That is called like training time. So with time, the error will decrease, and after some time, it will become constant. So either like if the model is simple, or if the data is simple, it may become to zero, just like we saw in the last class in that TensorFlow playground, right? The data, the error became completely zero, or it can become some constant. Okay, or similarly, same trend you can see an exponentially decreasing. So this curve is exponentially decreasing. Okay, so like this value and this value, there is no straight line trend, there is an exponential trend. So like if this value is suppose 8, then this value is 2, so it reduced by a power of 3. This value will be like 2 to the power depending on this distance. So it is an exponentially decreasing curve. You can think of e to the power minus x, or some any number with some power minus, because it is decreasing. Okay, so with number of epochs means how many times I'm again training and improving my data with the whole training data set. Okay, so first time it is like, first time I gave you tables from 1 to 20, and you remember this, just read them once and I will ask questions. Okay, so at first time you will be like, okay, you gave around 40% correct answers. I will say again, you go take and revise one more time, for all the tables. Again you came back, you gave answers to 50% questions. I told you, okay, you again revise only once. So third time you gave answer 60%, 70%, 80, 90, and after like 10 times, because up to 20, because up to the tables up to 20 is very easy, and like our brain is so improved. So we can reach an error of zero. Like after the 10th time or 20th time, all of you can tell me the table of any table that I ask without any error. But suppose I want to like remember all the prime numbers up to 10,000, right? Then probably with some error you can tell me. Okay, so epochs is number of iterations over the whole training data set. So this is what a bad model look like. So you whatever you do, when we will be building our model, we will see how my data error is increasing. Okay, so if it is increasing with repetition, that means something is wrong with my model. I need to change that model, or I need to look into the data. I need to explore what is causing the error, or I need to use some different strategy or a different model, not a linear regression model. Then I should go for multiple regression, or should I use decision trees? I should change that. Okay, this is if my error is increasing. So if I say every time you come back with that table, your error is increasing. So first time you gave 40% correct answer, next time you gave 30% correct answer, then then the third time you gave only 10% correct answer. Then I will say, okay, you tell me how are you memorizing, or how are you preparing these tables, remembering the tables. So some, like all of you followed the same trend by remembering or multiplying. Some guy came with another trick. Okay, I'm remembering the last digit of these numbers. Like if you ask 4 into 7, then I will do some trick, and if the at last should be 8, something like that. Some different method he must be using. That's why his error is decreasing with time. Sorry, increasing with time. So that means that strategy, that approach is wrong. We need to change that. Okay, so when we're thinking about overfitting and underfitting, we want to keep in mind the relationship of model performance on the training set versus the test validation set. So whenever you may ask, how can I check overfitting or underfitting? So for that, you need to check the trend of the error in the training data and in the test data. So what is the behavior of error in your training data and in your test data? Okay, so suppose this is your error, and with number of iterations the error is decreasing. It is perfect. This is what a good model look like. The trend of error in a good model will be of this shape. Error will decrease with time. Okay, in the training set. Right now, if I take the test set, so the test set should also, if my model is correct, if my model is actually capturing the underlying patterns of the data, then for that, even for the test set, the trend will look like the same. The error is decreasing exponentially with time, or and number of epochs. But so ideally the model will perform well on both with similar behavior. So for the training set, for the test set, the data should perform similar in the same way, similar way. But what happens if we overfit on the training data? So suppose my training data is overfitting. You remember that curve. Suppose this was my predicted model on the training data set. So for this, the error will be like this only, because error will be almost zero for our case, for the example that we saw. But for the test case, the error will go like this. It may increase initially, but it is going to then increase. It may decrease initially, but then it will increase. So whenever you encounter such a point, when you see like, okay, after these many iterations or with time, the error is increasing in the test data set, but it is decreasing in the training data set. This is an example of overfitting. This is the situation where should you know, okay, my model is overfitting on my data. I need to change something. Okay, so this is the time. This is a good indication of training too much on the training data. You should look for point to cut off training time. Okay, so I need to cut off here. So this means, okay, when you know your data is overfitting, there is no point of training again. Okay, so like if you train it for more 1 or 2 hours, 3 hours, or like any number of times, your model will always be wrong. So it's better you save your time. Just stop here, change some parameters in your model, and again try training, or just look at your training data once. Maybe your training data is wrong. Okay, so we will be like checking it when we are working on models. For now, we will look at evaluating performance of the model that we are building. So in all of the machine learning applications, we will be making a model. Okay, model as in we will be trying to mimic the actual behavior of data in terms of uh, some predictions, in terms of like what is the relationship between height and weight and marks. I want to predict my marks given the height and weight. Okay, so you just tell me height and weight, I want to predict the marks. So for that, such kind of a situation will demand a model. Okay, to to treat or to handle any real world situation, I need to have a model. Okay, Either some very old books of nature books should tell me, okay, sun will always rise from the east side at 5 o'clock, and it will set at 6 o'clock. Then I don't need any machine learning, because I know the model and I can observe, okay, yes, it is rising at 5 a.m. and setting at 6 a.m. So I know the model of sun. We all know the model of sun and moon. Okay, at morning, so we will sleep at night. So I know the model of behavior of my family members. Okay, but I want to know the model of my customer towards the company in terms of the expenditure and the kind of products he may want to buy. Then it a separate space. Okay, for that we need some data, right? Just like we know our parents from, like, by observing them, by knowing their nature, their behavior. Okay, if I ask my father to go out and watch a movie in the night with my friends, he will not allow me that, because I know his nature. So similarly, I need to know what is the nature of my customers if I am working for a online company, online e-commerce company. So we are looking at evaluating performance in case of classification. So classification is a type of machine learning problem or a situation where my task is to classify any object or classify any data into certain classes. Okay, so it can be classify this customer into, like, high value customer, medium value customer, or low value customer, based on the expenditure. Okay, so if some guy is spending 1 lakh rupees every month on Amazon, then obviously he is more important to Amazon than me, and if maybe some of you who are not spending 1 lakh rupees on Amazon every month. Okay, so he is high value customer, right? If some people who are spending around between 40 to 80,000, they are medium value customers, and who are spending less than the 40,000 are low value customers. So we probably come in the lowest end of low value customers. Okay, because we are whole in the whole year we are spending 10,000 or 15,000 rupees on Amazon. Okay, so this is how I can do these problems are called classification. One more example can be, suppose you are normal. I will give my model some pictures. My model should tell me whether it is a cat or a dog, cat or dog, cat or dog, right? So output is just one of the two classes, cat or dog. I will show the passport size picture of. So I'm making a model for this passport seva kendra. I will show the uh, photo in the passport to my computer screen. My computer should tell me whether it is a male or a female. Okay, male or a female. It should be able to tell the gender. So such kind of problems are called classification. So how can you evaluate? How can you say, okay, this model is correctly predicting, this is the error, this is not predicting correct nicely? Because how can you check the error in this case, right? So let's look at valuation matrices. Okay, so these are the four things that we look at. What is the accuracy? What is recall? What is the recall? What is the precision? What is the F1 score? Okay, so accuracy and precision we have, like, we use in general terms also, and they mean the pretty much the same thing. So you can look at this picture and you can tell what is, like, what how accuracy and precision varies. Okay, so, like, precision is simply your closeness of your each value, right? How your multiple values are close. Suppose, like, if you are bowling, if you ask you to bowl, I ask you to bowl 6 balls, and all of you are and, like, Arjun is bowling all the balls, like, with good length on the off stump, like all 6 balls hits the off stump. Then that means, like, he is very his precision is really good, and because all the 6 balls are hitting the wicket, that means his accuracy is also good. So accuracy is how close you are to the actual value. That is accuracy. And precision is how close your all of your values are to each other. Okay, so for example, say this. So this is like these black dots are the values, and this is my target point, central point. So if my values are, like, scattered all over the place and they are not close to the actual value, it is low precision. And it is not because all of these values are not close to each other also, that means they are low precision. And these values are not close to the central value, that means they are also low accuracy, right? If you see this graph, the values are not close to each other, like, they are close but not as close to each other. That means it is low precision. But the values are very close to the central point, or the desired point, that means it is a high accuracy. So this is high accuracy, low precision. This is low precision, low accuracy. And if you look at this point, See, all the points are very close to each other, right? So maybe if you are shooting an arrow or if you are shooting with a gun, then your barrel is somewhat changing. Some the barrel is at an offset because all the values, all the shots you took hit here. So the precision is really good, but your accuracy is bad because this is the distance between your actual goal and the your data point, right? So this is high precision, low accuracy, and this is the desired case: high accuracy, high precision. I want all the balls to hit the wicket, and I want all the six balls to hit the wicket, right? This is the best case, right? So if I ask my bowler to bowl on all the balls to the offside, and he's bowling all the balls in the offside, that means the precision is really good. And if I ask him to like hit the wicket every time, then his precision is also good and his accuracy is also good. So this case is the desired. So like let's understand in terms of like in how to do it mathematically for a data set, right? Right. So typically in any classification task, your model can only achieve two results. So basically in any classification class, so in any classification task, that is, I want to tell whether this person is gender, whether this person is male or female based on the photo. Either I can be correct or I can be incorrect. There is no other choice, right? My answer, so whatever my model says, male or female, so that answer can be correct or can be incorrect, right? So because there are only just two choices for this model gender classification, it is called binary classification. Binary means there are only two options for the output, whether male or female, whether boy, whether dog or cat, whether so in the case of high value, medium value and low value, it is not binary classification, it is tertiary classification, because I have three classes. So just it means how many classes can be in the output class. Okay. But for any kind of classification, my answer can have only two choice, whether the answer is correct or the answer is wrong. There is no medium answer, there is no like a middle way, right? Your answer is 40% correct, 60% wrong. This cannot happen. You treat this problem as an objective question, objective exam, whether your answer is right or wrong. It is not like 30% right or 70% wrong. Okay. So in our example, we will first attempt to predict an image, say is cat or dog. Okay, since this is a supervised learning, we will have first fit and train the model on training data, and then test the model on the testing data. When we have the model's predictions on the X data, we compare it to the true Y values, correct labels. So basically, since we want to classify the pictures of cat and dog. Okay, so I know that this picture is of cat and this picture is of dog. I want to build a model which will just see my image and tell me whether it is a picture of a cat and dog. Okay, and it is a supervised learning technique. Why supervised? Because I am telling the computer for 100 examples. Suppose I am giving the 100 pictures, I'm giving 100 pictures to the computer and telling them, okay, this picture is of dog, this picture is of cat, this picture is of dog. So I'm giving the computer labeled examples. Okay, where I'm telling the computer, okay, when you see this picture, it is a dog. This picture is a cat. So I'm giving the examples and the output values to my computer and asking them to, and I'm training it on those 100 pictures on the training data set. Okay, and when we have the model's prediction, we will from the X test. So this kind of nomenclature is used to address the training data set, because we are giving the X values. So normally we, like in mathematics also, we predict the Y values now. So Y term or Y is used for the value which you want to predict. Okay, and here in a classification case, I know, suppose you are showing a picture of a cat to a computer and computer says dog, then you can match, okay, for this picture the computer was wrong, because I know that